Okay, so we'll start our discussion of renormalization group today. Uh, so, let me say right in the beginning that whatever we will do is like the way we did it earlier is not exactly right thing to do, but a method which will tell you as to how one goes about doing a transformation of a particular kind, which is called a renormalization group transformation. And then, of course, we will realize that that's not the best thing to do, and then we'll try to improvise on that. And as we do successive improvisation, then we see how we arrive at the right kind of transformation. Okay, so let's try to see how we go about it. Okay, so the first thing that we will do is we'll work in real space and consider the usual spin system that we have been looking at, but in arbitrary d-dimensional hypercubic lattice. Okay, and what we are going to do is do what is called block spins. Okay, so I'll explain what that means. Okay, so so the idea is that we are considering a d-dimensional cubic lattice. It's called hypercubic simply because it is d-dimensional. If it was three-dimensional, it would have been called cubic. Okay, and the Hamiltonian is the same one that we had looked at earlier. That is beta h is equal to minus beta j, the summation over nearest neighbor interaction between the spin degrees of freedom and an external stimulus, in this particular case magnetic field H, which couples to the spins at every site. Okay, so the J tilde and H tilde are written by just soaking up this beta, just to simplify the expressions. Okay, fine. So what we are going to do is to assume that this hypercubic lattice that we have has a lattice spacing of A in every direction. That's why cubic. Okay, and we are looking at the system in the near critical region. That means the correlation length is much larger compared to the lattice spacing. Okay, fine. So in this setup, we want to kind of study this system, and what we will do is we will pick some integer L. Okay, this integer is sufficiently large and positive, of course, but not too large either. The number is such that L times A is much larger than the lattice spacing. That means this L is a count of number of lattice sites that we are picking at a time. Okay, but L times A is also not as large as the correlation length. So imagine that that the lattice size is of the order of say a few angstrom, 1 or 2 angstrom. Okay, and the correlation length is of the order of few millimeters, say, suppose. Okay, then there is like 6 to 7 orders of magnitude difference between them. Okay, angstrom is about 10 to minus 10 meters, millimeter is 10 to minus 3 meters, and L could be something of the order of like say 1000. Okay, then it is still 4 orders of magnitude smaller than the correlation length, but 3 orders of magnitude larger than the lattice spacing, and it's kind of a reasonable number to choose. Okay, so imagine we are choosing something like this. You don't have to choose L to be 1000. You could choose the L to be like 50 also. It is still reasonably large compared to this and quite small compared to that. Okay, fine. Now, what we are going to do is to pick a hypercube of length LA in all directions. That means in every direction we have L lattice sites inside this cube. Okay, so the linear dimension of this cube is L. Okay, with respect to the lattice spacing, and therefore the volume of that hypercube with linear dimension L times A is L to the D times A to the D, of course. Okay, and since at every lattice site you have a spin, the total number of spins inside this hypercube would be L to the D. Okay, now what we are going to do is to replace these L to the D spins by a single spin. Okay, so just to get a simpler picture, you could choose L to be 2. Okay, And then suppose you are looking in 2 by 2 in two-dimensional space, then what you are doing is you looking at 2 by 2 system, a single square, and you are going to choose those 4 spins there in 2 dimensions and replace those 4 spins by a single spin. Okay, and that single spin that you will put, which will replace these 4 spins, is the one which will be called block spin. Okay. Now, how do you write down this block spin? Okay, so that is the process of block spin transformation. Okay, and uh, I will explain it in a moment. But what is going to happen is the following: that if the initial problem had n spins, okay, where n is pretty large number, okay, then and you are working in say d dimensions, then for every L to the D spins, you are going to replace uh, that entire set by 1 spin. Okay. Once you have done that, then you pick up another L to the D spins and replace that by 1, and so on. If you do that, then the initial number of n spin goes to n upon L to the D. Okay. So that is how the number will reduce. Okay. So in the new lattice, which is has much larger spacing now, the initial lattice has a spacing of A. New lattice effectively have a spacing of L times A. Okay. So this lattice would have much fewer spins compared to the initial one. Okay. Fine. Now the block spins that we will write down, which are n by L to the D in number, okay, they are defined in the following way. You define SA. Remember the original spins were defined as SI for every lattice site I. Okay, new lattice sites will be denoted by capital A, and capital A runs from 1 to n upon L to the D, and they are defined as 1 over mod of modulus of ML times 1 over L to the D times sum over all I belonging to the block A. Okay, the spins at all sites I. Okay, so there are L to the D such values of I inside the block A. You pick the value of the spins at every site and just take a sum of that. Okay, divide by the volume of the block and divide by 1 over mod ml. Okay, 1 over mod ml is what we will define now. That is the average magnetization. And that average magnetization is basically just take the average value of these spins inside the block, okay, and take that sum and define ml to be that sum per unit volume. Okay. Now the reason why we are choosing 1 over mod ml here is because if you do that, then this quantity on the right hand side takes the same values that SI were taking. So suppose you had the spins which were taking values plus or minus 1, like the way Ising spins were, then SA also would take values plus or minus 1. Okay. If the spins was taking, more values like plus 1, 0, minus 1, then SA also would take plus 1, 0, minus 1. So this is just kind of a normalization to ensure that this number doesn't shoot beyond the limit within which the original SIs were defined. Okay. So that is the statement that the normalization ML ensures that average values of SA is plus or minus 1. Okay. Fine. Now, our initial problem that we started off with had nearest neighbor interaction. Okay. After doing the blocking, we have a lattice which is of much bigger size. The nearest neighbor locations are L times A distance away. Okay. And the next nearest neighbor is much further away because it is on the square lattice. It will be the diagonal, the first diagonal distance, which is 2 times, or rather square root 2 times L times A, and stuff like that. But what we will assume is that, like in the original system, the block spin system also has nearest neighbor interactions. Okay. If we do that, if we assume that, and if we ensure from this normalization that SA also takes same class of values that SI we are taking, okay, then the form of the Hamiltonian for the block spin would be same as the form of the original Hamiltonian that we had written down, namely this one. Okay, is the only difference is that we will replace SI and SJ by SA and SB, and as long as A and B are nearest neighbor, the interaction is there. Okay, only difference would be that J tilde and H tilde that we have written down in the original problem may differ for the block spin. Okay, so what we will do is we will call the new Hamiltonian HL because L was the integer that we used for constructing the coarse-grained system. So beta HL is equal to minus J tilde L times nearest neighbor interaction between SA and SB, where AB take value n upon L to the D, because that is the total number of block spins, minus H tilde L times summation over A SA. Okay, this form of the Hamiltonian essentially comes from this statement that the Hamiltonian, rather this statement that the block spin Hamiltonian again has nearest neighbor interactions. Okay. Now, if the initial problem had correlation length xi t, okay, then because of this blocking, with respect to the new lattice, the effective, so xi t was some integer times the original lattice size. But now your new lattice size is L times A. So with respect to new lattice size, the xi t would change. Okay, and in fact, in the process of doing the block spin, we would be reducing the correlation length. Okay, because the physical correlation length is not really affected. Okay, by the block spin transformation, but the unit with respect to which you are measuring the correlation length, namely the lattice size, that unit itself has increased. Okay, so therefore, initially, if xi was some large number n times a, then the xi L is n times a upon L. Okay, and therefore xi L is smaller than xi. Okay, but that means after doing the blocking, what has happened is that the correlation length is actually reduced. Okay, but that correlation length reduction means that you are actually going away from the critical point, because as you approach the critical point, correlation length seems to be going to infinity. Right? That is what is the definition of criticality, that the correlation length diverges. Okay, but block spins seem to be taking us away from the critical point. Okay, so therefore the block spin Hamiltonian HL is actually defining a system which is further away from the critical uh, uh, point, uh, whereas H was the one which was closer to the critical point. Okay, to put it a little differently, the temperature TL is less than the temperature T of the original system. Okay, and you are actually going, and T is already less than TC, so you are kind of little below the criticality, and you actually go further away by doing a transformation of this kind.
So,
Okay.
so
Yes.
yeah, I'm not really sure of the statement that we are going away from the critical point, because the actual value of xi is the same. If it was diverging earlier, it still will be divergent.
That is right. Yeah. So we are taking the value of xi to be finite actually, so that we are kind of in the neighborhood of the critical point. But this is a picture that the block spin would give you. Okay. That with respect to
It is
initial,
just that the distance will be like, it will look different, but it is actually
exactly.
the same.
Yeah. The realistic distance is still the same. That's what I'm saying. The physical correlation length is not affected. But with respect to block spin, it would appear that you are actually going away from the critical point. Right.
I mean,
Yes.
critical point is something physical, right?
That is right. Yeah.
Then how can just modeling say like we are going away from the critical point?
No, no, you are okay. Let me put it this way: that the xi hasn't really changed. Okay, it is just that the variables which are used for describing the system, okay, in those coarse grained variables, okay, the critical point is further away. Okay, that means you could do further fine graining in the system to actually approach the critical point. Okay.
Yeah.
So, so it's just a question of what kind of variables that you have used. Okay, if you had chosen the right kind of variables, you would have described the critical behavior of the system better than the kind of variables that we are using. Okay, we will use better variables soon. Okay, so it is not that we are actually moving away from the critical point. It is just that the choice of variables used for describing the system are coarse grained. So therefore, they are not able to pick up the picture of the system. Okay, we will see that this is not what we actually want to do. Okay. Okay, so let me just go ahead. So the effective magnetic field experienced by the block spin is what we will call HL, which is H times the average magnetization ML times the volume of the unit cell. Okay, and therefore the original interaction H times SI would be written as H times ML times LD times the block spin sum. Okay, and we would call this quantity HL. Okay, this relation actually comes about from here. Okay, so you can check that SIs were defined. The relation between SI and SA actually followed this relation. Okay, so if you use this relation back up there, okay, you'll find that your HL would be written in terms of H times ML times L to the D. Okay. Now, this is the kind of point First was talking about, that the free energy of the system is actually independent of choice of variables. Okay, so therefore, you should kind of be able to write down free energy in terms of, on the set of variables. Okay, number of degrees of freedom may be different in those set of variables, but the effective of physical observables shouldn't be affected. Okay, so if you have n degrees of freedom, okay, and you do block spin to go to n upon L to the d degrees of freedom, then you should be able to say that the total free energy of the system should be equal. Okay, so that would mean that n upon L to the d times the free energy written in terms of these variables. Okay, temperature TL and magnetic field HL, if F is a function of that, that should be same as n times the free energy with respect to temperature T and magnetic field H. Okay, and this would essentially mean that the F of TLHL is L to the D times F of TH. Okay. Fine. Now, the thing that we really want to get at is not the relation like this, but we want to get the relation between TLHL and TNH such that we can kind of realize an equation of this kind. Okay. This is just a statement that a physical observable is the same no matter what kind of degrees of freedom you use for describing it. Okay. So what we want to do is we want to ask how TLHL depend on the original set of variables. Okay. And since we are in the scaling region, we would assume that TLHL are related to TNH through some power law dependence on the scaling that we did. That means L to the some power times T would be TL, and L to the some other power times H would be HL. And if we do that, then we want to ask a question: how does this equation actually is realized when you do a scaling of this type? Okay, so we want to understand the relation of between TLHL and TH. Okay, so as I said, we will assume that we are in the scaling region and write down TL to be T times L to the YT and HL to be H times L to the YH. Okay, and we'll assume YT and YH to be positive. Okay, then all we'll have to do is to plug it into this kind of behavior, and we find that F of TH is, I'm just kind of taking the L to the d on the other side. So you get f of th is equal to L to the minus d times f of t times y, sorry, t times L to the yt and h times L to the yh. Okay. Now remember we had talked about functions which are homogeneous of degree d, and they would have a particular property under the scaling. So this is the kind of behavior a function of a homogeneous function of degree d would have had, and that there is a L to the minus d popping out if you do a scaling of the variables on which the function depends. Okay. So what we will do is that we can simplify this. This is something we had done earlier, that we said that, like, if you have a convex function f, which is a function of x, y, z, dot, 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 and then you take lambda x, lambda y, lambda z, this thing, then it would be written as lambda to the, say, minus d or plus d or something, times f of x, y, z, dot, dot, dot. And then what you could do is that you could kind of divide the whole thing by x, and then you write down a function which is function of 1 comma y by x comma z by x comma dot dot dot, kind of stuff. We will do the same kind of stuff here. That the transformation would correspond to saying that we are going to choose L in such a way that that for a temperature T, T to the minus 1 by yt would be equal to L. Okay, if you do that, then T times L to the yt would just be equal to 1. Okay, if you do that, then you can replace the L here by T. Okay, and then you get a relation which is f of ht, which is f of 1 comma h times mod t to the minus yh upon yt. Okay, and then L to the minus d would, through this scaling, would be written as mod t to the d by yt. Okay. We can then define yh by yt is equal to capital delta, and then stare at this expression and identify quantities that we know already. Namely, if you take the second derivative of the free energy that is related to specific heat, and specific heat exponent was alpha, so you can think of f as a double integral of the specific heat. Therefore, the coefficient, uh, the power law coefficient sitting in front would be 2 minus alpha, because it's a double integral with respect to temperature. Okay, so therefore you say that 2 minus alpha is equal to d upon y by d upon yt. Okay, and you can kind of use this fact to kind of determine yt in terms of some of the scaling exponents. Okay. Fine. So this is what I was saying, that this 2 minus alpha written here is basically following from the scaling behavior of the specific heat. Okay. Now we could do something similar with say 2-point function. So you can look at G, which is a function of RL and TL, and write that as a 2-point connected 2-point function with respect to the block spins SA, SB. Okay, and if you compute this, you could kind of ask how you would relate this G of RL TL to G of RT, which is written in terms of SI and SJ, which are the original spin. Okay. Now recall that, like, we had written down the average magnetization, which was ML. Okay, so maybe I should just go back a little, and so we have this relation coming from relation between SI and SA, the block spins, which gave us the factor like that, and which told us that HL is equal to H times ML times L to the D. So that tells us that the average magnetization can be written as ML is equal to HL times L to the minus D upon H. Okay, and we said that HL HL scales as H times L to the YH. Okay, so if you substitute that, then the h will cancel out and it will go to L to the YH. So that gives you ML scaling as L to the YH minus D. Okay. So we can use this and replace SA inside the block spin 2-point function by SI. Uh, and we know how SA and SI are related. Take those factors and you get a term which is 1 over L to the 2 times YH minus D. 2 because we are doing 2-point function. 1 over L to the 2D, which is a normalization for the spins sums out here. And now you replace SA and SP by SI and SJ. Okay. And when you do the averaging of that, for these spins over the blocks, you get the volume of the blocks in this computation, which cancels L to the 2D in the denominator, and you find that the 2-point function for the block spin is related to the 2-point function through a scaling factor L to the 2 times YH minus D. Okay. Now, what we are written here is the dependence on distance and temperature, but we could also add a dependence on magnetic field. And if you do that, then we can write G, which is R upon L, which is same as RL, T to the TL, which is T times L to the YT, and HL would have been H times L to the YH, and that quantity would be related by this factor L to the 2 times D minus YH times the original correlation function. Okay, fine. So again, we will do the same stuff. We'll choose L in such a way that this quantity can be set to 1. Okay, and if you do that, then you replace this L by the temperature factor, and you get the 2-point function GRTH written as T to the, so there's a small mistake here. I should have written this 1 in the middle because it's the T which is set to 1, okay, and not the H. But GRTH would take a form T to the 2 times D minus YH upon YT. This YT comes from this factor times G of R times T to the 1 by YT, 1, and H times T to the minus YH by YT. This term should have had a minus sign, but I have kind of pushed this L power on the other side and written this expression. That is why there is no relative sign between this. Otherwise, this minus sign would have kind of put a minus sign out here, but I have taken L on the other side. Okay, fine. So what we will do is we will define the G for the block spins to have a specific scaling property, namely it goes as R times T to the 1 by YT whole to the to this factor 2 times YH minus D times new 2-point function, which is written in terms of only these 2 variables. Okay. The purpose of doing that is that if you do this, it will soak up the T factor which is sitting out here, and G is related to this G hat only through the dependence on R. Okay, so if you do that, then you get G RTH is equal to 1 over R to the 2 times D minus YH times G hat, which is a function of the scaling variables R and H. Okay, but we know how this 2-point function is related, okay, from the scaling hypothesis. Namely, this 2-point function should go as 1 over R to the D minus 2 plus eta times G hat. We will have power law dependence like this. Okay, this delta we have already seen some time ago, that the delta is YH upon YT. We had seen a couple of pages ago. Here. Okay, so that factor comes out right. Okay, and the factor nu is in this particular case is just 1 over YT. Okay, so okay, so from this you can basically read out the scaling relations to minus alpha is a quantity that we had discovered some time ago. Sorry, so back again. Okay, which is d upon yt, but 1 over yt is new. Is something we just found out here. Okay, so therefore 2 minus alpha is d times nu. Okay, and gamma is basically nu times 2 minus eta. Okay, so so therefore what we get is that using these relations, okay, I mean any which way you work out, this is a relation that we adopted earlier. This is a relation that you could have determined by staring at these two expressions, or you can use these scaling relations to determine all these quantities. Okay. So what we find is that, like, in spite of it seems to be kind of giving the indication that the block spin takes us away from critical points, it's if we are within the scaling region, it seems to use it seems to be consistent with the scaling relation of the critical exponent, and tell us as to what kind of scaling that you need to do to relate the uh, physical observables in the original uh, written in original set of variables versus the block spin set of variables. Okay. Now, uh, this way of simplifying the system, of instead of studying large number of spin, you study small number of block spin seems very appealing. Okay, and you know, it also allows you to kind of give a description of the microscopic system in terms of some kind of average coarse-grained description in terms of fewer number of degrees of freedom. Seems quite appealing and kind of mm, intuitively uh, kind of good thing to do. The system still has kind of various problems, and because of which it actually is not the right thing to do. Okay, so let's see what are the things that we would kind of get stuck into in the process of doing transformation of this type. So the first thing that this process kind of does not tell us is how is the universality kind of getting set in. Okay, now this is something that we have been talking about uh, in this course, that you have multiple different models which look apparently quite different when they are away from criticality, like liquid gas phase transition versus binary alloy versus easing model. At least a priori, there doesn't seem to be anything common between these kind of models. In the neighborhood of criticality, all these models seem to behave the same way. Okay. In fact, I am giving few examples, but in reality, there are like infinite class of such models which have the same universality, universal behavior, and they belong to the same universality class. Okay. And this kind of way of doing block spin kind of transformation does not actually tell us as to how the universality would set in a system of this kind. Okay, so that seems like one of the very important shortcoming of the method of this kind. The other problem is that there is no first principle way of deriving what are the values of YH and YT in this setup. We basically use the fact that there is a scaling relation through which we kind of do iterative computation of what YH and YT would be. Okay. Uh, the third, and which is the most important, and something which is, Wilson basically discarded to liberate this process, was the assumption that the block spin Hamiltonian is identical to the original Hamiltonian up to some modification of the parameters. Okay, which seems very restrictive, and in fact, one of the you know important deviation from this kind of method that Wilson suggested was to abandon this idea. Okay, and to understand why this thing is too restrictive, let us consider one example. A simple example, just to understand as to why uh, uh, an assumption of this kind is too restrictive. Okay, so now of course the example that we are going to look at is already quite artificial and kind of seems a bit odd, but nevertheless it is useful to make this point. Okay, so consider a model where you have again a spin system, but there is no nearest neighbor interaction. Okay, but there is non-zero next to nearest neighbor interaction. Now you can immediately see why it is unrealistic. That you have spins which are on neighboring sides, they don't talk to each other, but next to the neighboring side would talk to each other. Okay, suppose for some weird reason we have a model of this kind. Okay, then if you do block spin on a model like this, okay, then you choose some L size, linear size kind of cubic block and replace that by a single spin. It would be very hard to kind of understand as to why a new block spin system, uh, why it would not have nearest neighbor interaction. Okay, initially we had no nearest neighbor interaction, but non-vanishing next to nearest neighbor interaction. And after blocking, you the original proposal would say that you would continue to not have nearest neighbor interaction, but will have next nearest neighbor interaction. It's kind of physically hard to imagine why such a thing would happen. Okay, so therefore, this kind of is like just two-line statement about the illustrative example as to why a assumption that the new Hamiltonian for the block spin would have the same structure as the old Hamiltonian in terms of which original degrees of freedom were interacting seems a bit odd. Okay, so in fact, what Wilson suggested was that uh, that after doing successive block spin transformation, in fact, the new Hamiltonian that you would write down for the block spin should be almost independent of the structure of the original Hamiltonian. So it doesn't matter what was your original Hamiltonian, final Hamiltonian would take a form after successive block spin transformation, uh, which would be essentially independent of how you define the original one. Now, if you think about it for a moment, then you realize that if a system is of this type, then universality will be built into it almost instantly. Because what this tells us is that, like, if you write down a system where nearest neighbor interaction or whatever any type of interaction that you would define in the microscopic variables, okay, that information, suppose if it gets washed out uh, in the process of doing block spin transformation, then the long distance uh, physics that is described by successive block spin transformation would probably wipe out all the information about the microscopic interaction and give you a kind of coarse-grained description for multiple systems for which microscopic interaction has no value and only long distance physics really matters. Okay, if that is the kind of thing happens, the system would automatically kind of get into a universal behavior. Okay, so but in the process of doing this kind of description is quite different from the conventional statistical mechanics description, simply because uh, what it tells us is that if you want to describe a statistical system by doing block spins and successive kind of transformation of block spin, is that instead of studying large number of degrees of freedom, which is what was the main point of the statistical mechanics, that you consider large number of degrees of freedom and try to ask how the large number of degrees of freedom would behave collectively. You don't need to do that. In fact, what you need to do is that you can uh, look at the system by successive block spin transformation and look at finite number of degrees of freedom uh, and ask how those finite number of degrees of freedom would behave, and they would still be able to explain as to how the statistical mechanics of large number of microscopic degrees of freedom was. Okay, so this is the kind of main departure from the statistical mechanics in the Wilsonian approach, that you can reduce the number of degrees of freedom of the system and still maintain the same physics that the original system had. Okay.
So
Of course, yeah.
in like in a crude way, earlier we have n degrees of freedom, capital N.
Yeah.
Now we
Yes.
have n by L to the d, like in our system. It could be
Yeah.
something else in some other
Yeah.
system, but
Yes.
we are reducing by some sort of a rescaling.
That is right.
Uh, Now, in things like when we take the thermodynamic limit,
Yeah.
that is valid when we have like n large systems. We take some n going to infinity somewhere implicitly down the line in our calculation.
Exactly. Exactly. Yeah.
Now, since we are saying that we are bringing down the degrees of freedom to a finite quantity,
Yeah.
we won't be able to do that.
No, no, no. So the thing is that like when you take n going to infinity, then the number of degrees of freedom are still large. Okay.
And so
When
you're saying that we haven't rescaled in the sense that L to the D still brings it down to some finite quantity.
no, 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 no. So what one is doing is the following: that you are taking n going to infinity, L also going large. Okay, but n upon L to some power. Okay, is a finite number. Okay, so you have to
Even in
figure
the
out
thermodynamic limit.
even in the thermodynamic limit. Okay, that
So,
you would want to. Yeah.
so we aren't going to do statistical mechanics with this problem in the sense of average quantities.
Yeah, yeah. So in fact, we would be doing renormalization transformations. So we would kind of, uh, okay. So let me put it this way: that what we will do is that we'll scale the system, uh, and then kind of write down the new Hamiltonian for the system. Okay, rewrite it in terms of original scale. Okay, so suppose you kind of take the lattice and you make that lattice size go from A to L times A, write down a new system. Okay, then now rescale L times A back to A and study the system. Okay, so this is how we are going to do these transformations. Okay, so when n goes to infinity, okay, you are actually keeping the number of degrees of freedom to be still infinite, really, in some sense. Okay, but you are still, while doing the coarse graining, the number of degrees of freedom continue to be very large.
Okay.
Okay, so it's a question of how you scale the system. That you are scaling L to the D in a particular fashion, n going to infinity, and you want to ask a question as to how you would take n upon L to the D. Okay, you want to keep it large or you want to keep it finite. Okay, depends upon how you do this transformation. You would take different limits of the system. Okay, if you want to study thermodynamic limit of the system, you would continue taking n large, and n upon L to the D is still large. Okay, such that the total number of degrees of freedom is continue to be large. Okay, so for example, if you are trying to do something like this in say quantum field theory, okay, then what you would do is that like you would integrate out very high energy degrees of freedom and write down a theory in terms of uh, low energy degrees of freedom. Okay, but even if you do that, it's a continuum theory. So the low energy degrees of freedom are smaller in number compared to the high energy degrees of freedom. High energy modes or high frequency modes are integrated out in that sense. Okay, but nevertheless, low frequency modes are still infinite in number. Okay, so something similar will be done here.
Okay.
Okay, fine. The other important effect that uh, original block spin system or transformation told us was that the coupling constants, which are kind of something which are fixed numbers initially. Okay, the block spin method as well as this method where you allow the Hamiltonian to change uh, tells us that the coupling constants are not constants, but they are functions of length scales. So as you try to study system at some energy scale, you see the coupling constant to take some value, but at some lower or higher energy scale, the coupling constant would take a different value. Okay, and you would want to understand as to how the coupling constant changes as you change the energy scale in the system. Okay, So this is another new ingredient that the renormalization group or block spin renormalization brought in, which was not uh, there in the initial description of the system. Okay. So let's try to consider this in the Landau-Ginzburg perspective. Again, this is not going to be the right thing to do. We will kind of revert back to the spin system to understand as to what we need to do. But but let's try to see how we will kind of encounter a hurdle in the Landau-Ginzburg picture, and then we'll kind of redo the computation. Okay. So so far when we are studying Landau-Ginzburg description, we said that the order parameter of the system was spatially homogeneous. Okay, we always had our order parameter taking constant value. Okay, but what we could do now is that we could say that like order parameter could vary in as a function of space, and so therefore instead of writing phi, we could write phi as a function of x. Okay. Uh, Okay, so so suppose we want to try to do that. Okay, then one important thing that this would lead us to is that besides you know phi being a constant quantity, which should have been useful in determining how the interaction term or the potential in the Lagrangian of the Landau-Ginzburg model was, we also need to look at how the kinetic term would be. Simply because if phi depends on x, then the gradient of phi is non-vanishing. Okay, and therefore we need to incorporate that piece. Okay, so now we of course know that the correlation length, correlation functions would kind of have a long range uh, behavior in the neighborhood of the critical point. Uh, okay, um, and because of which we had initially assumed that the order parameter would not vary significantly over a large spatial region, and that that is something which was kind of something we had observed, that the magnetization remains constant over large distances. Okay, and that was our initial reason for assuming in the Landau-Ginzburg model that the order parameter is independent of space. Okay. Now, what we'll do is that we will try to do something similar to block spinning, but in the Landau-Ginzburg model. Okay, so we will choose some scale. Uh, so lambda would be the energy scale, such that 1 over lambda is less than the correlation length psi. Okay, and and if you do that, then remember the correlation length is a length scale over which the order parameter does not change significantly. Okay, so if you choose the size of the block uh, smaller than the correlation length, then it would make sense to assume that your order parameter is roughly constant within that block. Okay, so so this would of course mean that if you are in the neighborhood of the critical region, then 1 over lambda is much larger than the lattice spacing. Okay, the linear size of the block is much larger uh, than the lattice. Okay, fine. So as I said that if since this quantity is much we are choosing to be smaller than psi, we can assume that the magnetization in each block is roughly constant. Okay, and if you do that, then you can define the local magnetization by just summing over the spins within that block. Okay, uh, so n lambda is just a total number of spins within the block. Okay, now this definition is a bit kind of sloppy in the sense that like it depends upon how you define the block, how you define lambda, and so on, particularly in the Landau-Ginzburg model. Okay, but this process is what is called the coarse graining. Okay, and the coarse grain version of the magnetization M lambda would make sense as long as you take the take 1 over lambda to be smaller than the scale over which the order parameter does not change significantly. Okay, so all these processes are defined within the Landau-Ginzburg model to try to kind of maintain the basic tenets of the Landau-Ginzburg model, namely that it preserves the symmetry of the system, but while preserving the symmetry of the system, the order parameter really does not change significantly, and therefore you try to do a coarse graining over only that much range of the space over which the order parameter does not change significantly. Okay. So generally, this is what I was trying to say, that generally in Landau-Ginzburg model, we assume that it is slowly varying function, and therefore, you can kind of think of that as kind of a function written in terms of wave number with large wavelength. Okay. Right. So the idea is of introducing lambda is to just kind of ensure that there exists another length scale, okay, which is an important length scale in the process of coarse graining. Okay, and the way it appears in this computation is that if you say that your order parameter phi is not just a constant, but it also kind of depends on space, then your Lagrangian density is not just a function of the potential which depends on phi, but it's also a function of the kinetic term. Okay, because phi can vary from x and x plus delta. Okay, where of course delta is of the size of the blocking that you are doing. Okay, fine. Now, if you take a continuum limit of this, it will again actually give you a Landau-Ginzburg energy functional, and that's where the whole problem is. Okay, and that is the reason why, in fact, that is the reason why I was saying that the Landau-Ginzburg method that we are trying to do is not going to be quite correct, and we'll have to kind of revert back to the spin system. And the reason is the following: that when you take a continuum limit of this, then the coarse-grained energy functional that you would get for the Landau-Ginzburg system, okay, will not have the structure which is similar to the Gibbs free energy. Okay, so let me see if I have a picture of that, maybe on the next page. Okay, so the thing is the following: that remember in the Landau-Ginzburg model, we had this potential, and this potential would have a structure which is of a single well if you are above the critical temperature, and it would be a double well when you are below the critical temperature. Okay, and a potential which would be of more of a double well type is clearly not a convex function. Okay, and if the variation of the order parameter is very small, then this quantity is not going to overwhelm this double well picture of the potential, and therefore the potential will continue to dominate if these changes are not significant. Okay. On the other hand, Gibbs free energy is a convex function. Okay, and because of that, there is no direct relation between the energy functional that you would get from looking at the expression like this for the Landau-Ginzburg model and the corresponding Gibbs free energy. Okay. The other thing about the Gibbs free energy is that it does not depend upon how the order parameter depends on the spatial coordinate, because it's just a thermodynamic quantity and does not really kind of depend on these kind of details. Okay. On the other hand, the potential would of course depend on how phi would depend on x, because besides this, it would also have additional kinetic energy contribution coming from a term like that. Okay, so I shouldn't say V, but more appropriately L. Okay, so Gibbs free energy would have a structure which would be like this. Okay, it's a convex function, whereas the Landau-Ginzburg functional would look something like that. Okay, and clearly, you know, Landau-Ginzburg energy functional could not be used for giving a thermodynamic description of a system where you would expect the function to be convex. Okay. So the way to remedy this is to actually revert back to the spin variables and ask as to how you would do blocking in the spin system such that the the free energy of the system to uh, continues to be a convex function. Okay. So what we'll do is that we'll go back uh, from the Landau-Ginzburg degrees of freedom back to the spin degrees of freedom, and while doing that, we will say that the order parameter that has been defined in the Landau-Ginzburg model is defined over a block. Okay, and therefore you replace S, phi lambda by spins belonging to the block within which all the spins takes roughly the same value and which is equivalent to the order parameter value. Okay, so uh, so so we define S omega to be the representative spins which tell you what is the value of phi lambda in the Landau-Ginzburg variable, and for every such uh, set of S omega, okay, you have another set of spins which differ from this S omega, okay, and they form their own set of blocks. So you divide the total number of spins into block spins, okay, and sum over the blocks. Okay, so this sum is really sum over the blocks, and this sum is sum within the block. Okay, so what one essentially ends up doing is to write down the partition function where this description of L of phi lambda is already sum within the block, okay, and then you try to do a sum of this quantity over the block, okay. So this is what we want to do, okay. So we'll eventually kind of forget about this and go back to the spin and rewrite the system in terms of spin degrees of freedom, okay. And the main point which differs from the Landau-Ginzburg description as well as the block spin description is that uh, while we follow the Landau-Ginzburg idea that we preserve the symmetries of the model, we do not necessarily preserve the form of the Hamiltonian. Uh, like in the block spin, we will do coarse graining, but we will not maintain the form of the Hamiltonian. Okay, so those are the kind of things where you pick one concept from one side, like symmetry from the Landau-Ginzburg side, and coarse graining from the block spin side, and combine the two, but not keep the form of the Hamiltonian same, which is what was done in the block spin case, and similarly kind of uh, not keep the order parameter to be independent of space as was done in the Landau-Ginzburg case. Okay, so let's try to kind of yeah, maybe I can define this coarse graining renormalization procedure next time. Would that be okay? It's already 4 o'clock.
Yeah. Could you go back to where we defined the lambda?
Yes, sure. Yeah. Yeah.
Yeah. Okay.
So what we are saying is that, like, the reason why I'm defining 1 over lambda is because of you know uh, kind of catering to both set of people. Uh, when you do quantum field theory renormalization group, you actually do a momentum cut off on the upper side. Okay. Uh, the when you do real space renormalization group, you do a spatial cutoff on the lower side. Okay. So writing 1 over lambda means that lambda is an energy scale. Okay, but 1 over lambda smaller than xi tells you that, like, you are taking the larger cutoff, but not as large as the scale over which there is a coherence.
Okay.
Yeah, sorry, it is a bit hybrid, but at some point they will all mix actually. They are all related, in fact.
So, uh,
Yes.
uh, I mean, when we define this block spin method,
Yeah.
we wrote the Hamiltonian in the
Yes.
same form as in the usual
Original. Yes.
original form, but
Yeah.
we did not use it explicitly to derive or like any of these scaling relations. So why is it
Uh,
important?
why is what important that the structure remains the same?
Yeah, I mean, why
Okay.
are we using it as an information here? Where are
Uh,
we using it as an information to
yeah.
derive the scaling relations?
For example, how HL is related to H depends on the assumption that this Hamiltonian has not changed its form. No. Remember, like for example, this relation. Okay. That
Okay,
H summation SI is equal to some more block spin with L to the D times ML factor. Okay. Assumes that the final structure is going to be the same. Okay. And therefore the final Hamiltonian is going to look to be of the same form. Okay. In fact, we are going to abandon this idea. Our next In the next class, we are going to have a new Hamiltonian which has a term linear in S, quadratic, cubic, quartic, all kinds of terms. Okay. We Initial model has nearest neighbor interaction with binary interactions of this kind and a solitary interaction with the external field. But the block spin Hamiltonian or RG Hamiltonian has all terms. Uh, two spin, three spin, four spin, n spin, you know, everything. Okay, as long as it preserves the symmetry of the system. Okay, so and that is what liberates the thing. Uh, in fact, the whole idea is to say that that the system is under control if the total number of independent data that you need to provide, like for example in this model is two, J and H value. Okay, there are only two parameters that your theory has. If your final model that you write down, let's call it H hat, okay, then that H hat model, which is done by doing series of renormalization group transformation, contains all kinds of terms. Summation SI, summation SI, summation SI, JSK, SI, JSK, SL, dot, dot, dot. Okay. They will have coefficients like, J1, J2, J3, J4, and all kinds of stuff. Okay. Uh, all those J's from, let's call them JA, A going from 0 to infinity. Okay. If they depend only on two uh, values J and H, okay, then they effectively do not have any additional information than what original J and H had. Okay, and our task is to actually determine those functions in terms of these functions. Once you determine that, then those class of models give a description of the entire system. Okay, whereas what this assumes is that you don't get anything beyond J uh, tilde and H tilde and nothing else. Okay, this is, I mean, nothing wrong with this. If you have a highly symmetric system, if your system has too many symmetries, then your Hamiltonian will be so much restricted by the symmetry that you can't write down anything beyond this. Okay, and in that case, of course, what you are doing is right. But the point is that, like, many systems are not that symmetric. The systems do have symmetries, but they are not so restrictive that they wouldn't allow anything else. And by demanding that your Hamiltonian retains its form to be exactly this, we are actually losing out on possible other terms that we could have added to our Hamiltonian and had maintained the information of the coarse of the fine grained system in a coarse grained model. Okay, so that was the hurdle actually. It's not like this is totally wrong. This would be right in a system in which you know there is just so much symmetry that it wouldn't allow you to do anything. Just to give one silly example, well, not silly, one celebrated example really, but is that highly supersymmetric quantum field theory called N equals 4 supersymmetric Yang-Mills theory has, total number of supersymmetric charges are 16. Okay, and that supersymmetry is so much that whatever you can write down consistent with that symmetry is all that you can write down. Okay, something simple like F mu, which is like a term that you would write down for the electrodynamics. Okay, as a Lagrangian, you can't do any modification on that. Okay, this symmetry completely fixes that stuff. Okay, nothing more than that is available. This statement is pretty much of that kind, saying that like uh, that the Hamiltonian wouldn't change its form. Okay, excepting changing the numerical values here. Okay, which is what would happen in n equals 4 supersymmetric gauge theories. Okay, but most of the other systems, rather, this is like, I can give you really one example. Barring that example, most of the cases, these things change. There are a lot many new terms that you need to add to get a nicer description of the system. And what Wilson basically pointed out was something even before supersymmetry was discovered, was that like that you should kind of allow all kinds of terms. You should only respect the symmetry of the system. Okay. So what has happened here is basically we restricted this by demanding that this interaction would retain its effective form. Is that okay?
And one more thing. In the end,
Yes.
are we going to have one kind of Hamiltonian for one kind of universality class?
Yes, effectively.
Okay.
So a given universality class has a kind of Hamiltonian. Okay. Other universality class has its own class of Hamiltonian. That's how it would look like. So large number of models, they don't even seem similar to each other. Okay, but their critical behavior is given by the same Hamiltonian. Any other question?